For 3 centuries, the Renaissance drove renewed interest in classical philosophy, literature, and art. As the third wave of the internet washes over the technical foundations of digital business, there's renewed interest in classical infrastructure, compute, network, and storage capabilities, particularly at the edge of the network. I've been having discussions with the authors of Enterprise Architecture for Digital Business. And in this discussion, I'll be speaking to Joel Moses, Distinguished Engineer and Chief Technology Officer of Systems at F5. He's the author of Chapter 2, An Infrastructure Renaissance. He explores infrastructure and the standards that will impact the future of infrastructure architectures, like the ecosystem forming around ARM architectures. He talks about 5G and container-native workloads. He uncovers the hidden advantages of the XPU industry, which is driving unprecedented power into the edge. Most importantly, he will examine how organizations can take advantage of these advances in a digital enterprise architecture and how public cloud and edge computing play a significant role in a modern view of infrastructure. It's always a pleasure to chat with Joel, and I hope you enjoy this discussion. Hey everyone, I am joined by Joel Moses. Joel is a distinguished engineer at F5, and he's also the Chief Technology Officer of Systems and Platforms. And on top of that, he's also an author of one of the chapters of this book, Enterprise Architecture for Digital Business, Chapter 2, which is an infrastructure renaissance. And Joel, we're going to be talking about what you meant by that. And let me first start off with giving you a moment to just kind of give us a high level of what you think this chapter kind of is going to deliver for folks.
Sure. You might have heard that software is eating the world. And that is definitely the case. But software without hardware is actually nothing. Software has to have a place to run. And doing things deliberately, choosing architectures deliberately based on the characteristics of hardware makes software run better and makes it eat the world faster. And so the chapter is an attempt to explain why you should take hardware into consideration as an application architecture component.
So one of the things that is mentioned, and I've had some chats with Lori McVitie about this too, another author in the book, is all of the XPUs that we have these days. And we've named a few of them at this point, but can you actually define a few of these, because they're going to come up throughout the book a little bit?
Sure. Honestly, there's a little bit of marketing that goes on when people name things, but the processing unit, and this hails from the landscape of graphics processing units, GPUs, which are used by certain applications for compute. There are other types of assistive compute that are emerging now. Some of them are called IPUs or DPUs, data processing units, or infrastructure processing units, and what those are called depends largely on the vendor that's manufacturing the component. But really what you need to know about this landscape is these are what I call domain-specific compute accelerators. They don't necessarily do everything, but they do very narrowly focused things very well. They assist in analysis of big data projects using something like a TensorFlow core or a TensorFlow subprocessor, or they may be very good at stream processing. The capabilities are in some cases unique to the card or to the CPU that's performing the task, but these are domain specific. They're not designed for generic tasks. They're designed to be very good at very narrowly focused tasks.
So now we're in this world where we have lots of options around very specific compute options. We also have a lot of options around where this compute happens. We have options around who manages this compute, whether it's yourself or you've actually brought on a cloud provider to provide some of this compute. Like, tell me, how do you think an organization needs to look at broadly? How do you architect all of these options to be able to take advantage of them?
Well, it's a difficult thing, actually. If you're working with big data projects, you're probably familiar with things like Doka for GPU assist, so that you can use NVIDIA GPUs to help you through vector analysis of certain data. And those are great. They accelerate AI and ML workloads, but in large part, you have to craft your application to be specific to specifically use that type of hardware. We're hoping to produce some things that allow you to do stream analysis on data streams that come through networking tasks. We're very good at that. F5 has had a long history of designing specific hardware platforms. In our case, appliances that have FPGAs and crypto processors that are domain-specific compute processors that allow us to deliver application services very, very quickly. The great thing about it is because we've had all of this history with programmable infrastructures, these things are being built into cards and built into to commodity servers these days, and so we're looking forward to the day when we can take something from a vendor like an IP or a DPU card and configure our services to work exactly the same, and in some cases with superior performance to things like appliance platforms that we've worked with over the years. It also allows customers to have a degree of flexibility to how they choose to instrument their applications, and gives them a guaranteed performance level on the hardware that they choose for the task that we're asked to perform.
Oh, so that's going to be interesting then. Like as people are selecting where certain tasks are going to run, and they're selecting based on the type of processing unit. How early on in the architecture do they need to consider this? Because it sounds like this is moving very quickly, and so something that you're developing that might take 2 years down the pipeline to actually have a product out there. Can we anticipate that there's going to be an XPU for anything?
I think that day probably is coming. The cost of infrastructure that supports applications and the cost of the infrastructure that the application runs on, or the compute for the application. We've actually been told by companies like Meta that in some cases they are finding it more expensive as they broaden out their use of AI and ML. The compute that runs the AI and ML has to be highly clustered. And that clustering operation is a networking operation. And that networking component and that networking operation is getting to be more expensive the larger those clusters get than the operation of the cluster itself, the compute itself. And so GPUs, IPUs, XPUs of this stripe offer a high degree of desirability to customers like that have an immense scaling operation that needs to be performed. And what they really need is they don't need to spend general purpose CPU on it. They need something very specific, very custom tailored, very low power, very high throughput. And so these things are starting to become part of their design. How early should you consider this in your design process? Well, this is an emerging technology. I think you should begin considering the ramifications of creating a separate infrastructure processing network that is run from this type of infrastructure from your general purpose compute that serves your application or your data. I think you should begin thinking about that right now. I personally think that you should think about domain-specific compute in the context of your application. However, beginning now, whether you can use GPUs to assist you in AI and ML workloads, this is something that you should definitely consider. You should consider it for a number of reasons, but primarily among them is the economics of it. General purpose compute is generally expensive. Domain-specific compute or using GPUs to assist offers an order of magnitude better performance, but it usually involves half the cost.
When you say half the cost, do you think that's something that's realized immediately, or something that has to be kind of recouped over a certain period of time?
Yeah, I think it recoups over a period of time, but it does so in two ways. One is that you can reduce your amount of general purpose compute that you provision. So that helps you contract the base cost over time. The other thing is that a lot of this assistive compute is built on lower power platforms, things like ARM processors that perform the same basic level of performance at much lower power requirements. So you also get a savings on the electricity needed to run that type of an architecture.
Yeah, that's interesting too, and that's a great point. Everybody is probably concerned about power and space these days as we scale out these infrastructures. And then maybe one last question for you. You know, it sounds like XPU conversations kind of dig into the weeds, but from a leadership perspective, for a CIO, a CTO, why should someone at the C level be concerned about XPUs?
Well, first of all, it's an emerging area of technology, and it involves assistive compute, and it also targets something that I think is beginning to happen. We've been governed in the world of hardware by something called Moore's law for a long time. That every year you're going to get an order of magnitude increase in the performance while the price continues to drop of general purpose CPUs. We're getting to the point where we're almost bumping up against the laws of physics. We have processors that are being produced in smaller and smaller nanometer process, and at some point, we're going to run into a physical wall with some of those things. Now, a general purpose CPU is designed to do everything. It does everything at a fairly, even keel, a medium level of performance. When you begin designing processor environments that don't do generic things, but do very specific things like crypto acceleration or stream processing or TensorFlow or vector math, these things oftentimes perform much higher, but do a lot less. And the power requirements are less for those. And so the domain-specific compute hardware is an attempt to kind of keep on progressing in the state of compute without getting into trouble with the laws of physics. GPUs, IPUs, XPUs, etc. These are things that will help us extend the life of Moore's law.
Yeah, that's cool. Well, you heard it here, folks. If you're a CTO or CIO and your architects come to you asking for some money and budget for XPUs to play with, you should probably listen to them, give them an opportunity to do some exploring there. It was great to have you on, Joel. Everybody who's watching or potentially listening right now, we should have links in whatever description box is available on the platform that you're watching from or listening from to go check out this book. Again, that's Enterprise Architecture for Digital Business. And thank you very much, Joel, for joining me today.
Absolutely. Great to be here.